In these couple examples, this is very similar to just finding the derivative of a function. We're just going to add a couple steps to the end to actually create the equation of a line. But we need to find the derivative and evaluate it at the x-coordinate of the point so that we may find the slope of this line, as that's what derivatives give you if you substitute in a number for x. It gives you the slope of a tangent line. So the first function over here, f of x equals x plus 1 over 2x minus 3 at the point, we're trying to find the equation of a tangent line at the point 2, 3. So the first thing you need to do is find the derivative. So when you go through and find the derivative of this function, it'll look something like this. Negative 5 over 2x minus 3, the quantity squared. From here, the function the derivative needs to be evaluated at the x-coordinate of the point that's given. So here I'm going to substitute 2 in for x. Get negative 5 over 2 times 2 minus 3, the quantity squared. So there's your 2. And when you simplify all this out, you will get that the slope is negative 5. This is the slope of the tangent line, negative 5. This in mind, you can write the equation of a line, and I prefer the point slope form. So that's y minus y naught equals mx minus x naught. And with this, you get these values, x naught, y naught, from this point right here. The first coordinate is your x naught, and the y coordinate is your y naught. So you just substitute these numbers in here. That'll give you a 2 here. Oops, that's not where the 2 goes. It'll give you a 3 here and a 2 here. And y stays y, and x stays x. And the slope is right here. This is what you spent your time finding the derivative and substituting the number in. That gives you the slope of negative 5. So this line is very, very acceptable for the equation of a tangent line. If you like the slope-intercept form, you can always solve this equation for y, distribute the negative 5, and collect like terms. That looks like this. Y equals negative 5x plus 13. So there's your answer for the slope of the tangent line at this point on this function. For this other example over here, again, the first thing you need to do is find the derivative of this function. And when you do that, you'll need to use the product rule. You can see there's an x times the square root of x squared plus 5. So when you find the derivative using the product rule, it will look like this. Here is the derivative in all of its ugly glory. This looks atrocious. And you may have just seen a video, or will see a video in a little bit, that states that where I state you need to find the derivative and simplify. Well, those are the directions for those problems. This derivative, we don't need to simplify at all because the goal is different. We're trying to find the equation of a tangent line. The derivative is just a means to get us the slope of that tangent line. Now I see one thing here that I would like to simplify, actually two things, and that is in this first fraction and this only fraction that you see. These 2's will cancel, and this x I can multiply over here and have x squared. So those two things I think will make the computation portion of this finding out what the slope is when x equals 2, it'll make that computation a little bit easier. So the next thing you need to do is go through and find f prime of 2. So that will look like this. You want to have 1/3, and in the top will be 2 squared over 2 squared plus 5 to the 1/2 power plus 2 squared plus 5 to the 1/2 power. So I can simplify this further to say it is 1/3 times 2 squared in the numerator is 4. Here, 2 squared is 4 plus 5 is 9. A half power is a square root. Square root of 9 is 3. Plus, we just did this calculation right here. 4 plus 5 is 9. Square root of 9 is 3. So when you go ahead and simplify all of this stuff, you'll get that the slope is 13/9. So this is now the slope of the tangent line. And then by following a similar method over here, we have the x0, y0 values over here with a slope of a tangent line. You'll get two equations that look like this. So this is how you find the equation of a tangent line to the graph of the function at a given point.